we're looking at these ones are constitutional isomers because they're completely connected differently. So here we have one butene. Here we have the double bond is in the second position, 2 butene. And then these are called stereoisomers because the double bond is in the exact same spot. But remember, we can't rotate a bond around that double bond. We can't rotate the molecule. So this is called cis-2-butene because these 2 methyl groups are locked on the top. They're on the same side. So if they're on the same side, that's called a cis molecule. If these, so this is the same connectivity, but this molecule is locked in the trans position. They're on opposite sides. These methyl groups are on opposite sides of the double bond, so that would be trans-2-butene. So the only difference is the 3D arrangement. Either the methyl groups are locked on the same side, or in trans-2-butene, they're locked on the opposite side. Do you see that pattern? Okay. That's called a stereoisomer.
Oh, yeah.
There you go.
What's up?
Inside joke.
Oh.
You forgot it. Gonna make you sad for a little bit.
Oops.
You can't say that either.
I don't care.
I don't even think if I ever even had an inside joke with any of my friends.
Oh, really?
No, being for real.
Yeah, that's how it is sometimes. I don't know what to think about.
That sucks, I guess.
Oh, just letting you guys know.
Okay, we talked about this. So this is the difference is if they're locked on the same side, that's a cis molecule. If they're locked on the opposite side, that's called the trans molecule. Okay, so this is a molecule that you might have heard of before. Have you heard of oleic acid?
Is it for hair growth?
Oh,
Or am I tripping? I'm
maybe
Oh, right.
I feel like I've seen it in the.
I think so.
oleic acid. Okay, this is like a common biomolecule, oleic acid. So this molecule is locked in the cis conformation because they're locked across this double bond. Does that make sense? They're on the same side of the double bond.
Yeah.
And then these hydrogens are on the other side. They're on the same side. So these long chains are on the same side. The hydrogens are on the same side. Okay. So if we have, so this is like the same molecule, but it's either locked on the, so this would be the trans position because they're on the same side. The groups are on the same side. Cis, they're on opposite, cis, they're on the same side. Trans, they're on the opposite side. So one's poking up, one's poking down, one chain, okay? And then this one is a saturated hydrocarbon with the same number of carbons on there. So, have you ever heard of a trans fat?
Yes.
Yeah? Okay. Or the other option is a cis fat. So if we have a trans fat, those molecules, the longest branch is locked on the opposite side of the double bond. And those are harder for our bodies to process.
Oh.
And so just this conformation, this different stereoisomer makes it hard to break down. And then this one, oleic acid is unsaturated fatty acid, and it's in olive oil. Yeah, maybe, yes, it probably could be in hair products.
Eyebrows do that. Shiver.
So, anyways, that is the real world application of trans isomers. Okay, go ahead and see if you can draw these. We talked about molecules with double bonds. This is the same molecule, but one is in the trans position and one is in the cis position, locked across the bond.
The last 3 slides.
Oh,
See if you can draw this.
That's just molecules.
Yeah, what about the trans?
That's all you got? What did you get for trans?
So it just means it's like locked on the other side. So no, it's locked on the other side. So it's like
So it'd be like this.
diagonal. And then
Diagonal. And then this one's
it's
like.
like V-shaped. That's just how I put it. That was unintentional, I just wanted to know.
What was unintentional? Oh, okay. It's like the cysteine channel.
I don't know if that's the same prefix.
So bad.
So that's the cysteine channel.
No, it's not like this is tea.
I don't know what the cysteine channel is. Isn't it that really big one in France?
I think so. I
The
think.
one that they're building for like 30 years. What's the cysteine channel? Oh, what's the one in France? It's not spelled like that. Right, that's it. Yeah, I don't know how to draw these.
Yeah, that's what I was thinking.
Remember. That's just crazy. You help him with the track.
No.
You're just not gonna be there.
You just don't want to be there.
No, I actually have something.
You just want to go home.
No, I legit have something.
I don't believe you.
There's a freaking ant on my leg. Crap.
What, really?
Yeah.
Was there really?
It's right there.
What the hell is it? What?
There's a cord on my leg.
How? How did you?
Oh gosh. Larry will miss out a great time.
Okay. So let's try this one. I'm gonna draw this one up here and you can tell me if this is what you got. So we have pentene. So I'm gonna go. Oh, I have to check my pen. Turn on. Pentene. 1, 2, 3, 4, 5. And then the 2 means the double bond's at the 2 position. And then we have a 4 at the methyl group. And so then this, it says trans 4, oh 4, let's see. 1, 2, 3, 4. Okay. So we have a methyl group 1, 2, 3 here. So then the way I drew this, the longest groups on the double bond are on opposite sides. Or the biggest groups across the double bond are on opposite sides of the double bond. So what I'm looking at is if I draw a dash between my double bond lines, there's the long group on the top and a long group on the bottom. So this would be the trans version of the molecule. Okay, so then the cis, they have to be up.
Diagonal.
So you just have to take this one and flip it up here. So it's the same molecule, you just have to rearrange so this is not pointing down, it's pointing up so it's on the same side. Or you can flip this down. This is a smaller piece, so I'm gonna flip that up. So I'm gonna draw the same thing. 1, 2, 3, 4, and then this part can go up. This is the double bond. 1, 2, that's the 2 pentene. 1, 2, 3, 4 methyl pentene. So then if I draw my dash through this double bond, these are on the same side. So that's cis, they're on the same
Okay,
side.
so it would just have to be parallel technically, or what would you, how How would you help me understand it? Because I have to have it in more simple terms.
They're
To
on the same
understand
side of the double bond. I don't know. Not parallel. They're like making it
I need it in
the
super.
trapezoid again.
They're pointing in the same direction.
Yeah, they're pointing in
Okay.
the same direction. So this one, this
Yes.
is like our. Oops, my pen didn't like that color. Do you see our? These are on the same side. We're making a trapezoid.
Oh.
These are on opposite sides.
Okay, that makes sense.
Okay.
One second to draw this.
Okay. Yep.
I got it.
Okay. All right. This is we have to imagine what's going on. We have to decide. Can we have? We have to imagine how they gave it to us, and then have to imagine flipping one side and seeing if we can get it to be either cis or trans. And if it could be a cis-trans isomer pair, then we click yes. If there's the same groups on one side, so like this one can't exist as a cis-trans isomer because we have two hydrogens. So if we rotate that, it doesn't matter. There's only one group that, so like this one could be Cl up, H down, H down, H up. So if we flip this, that's going to be the same molecule. Okay, so that one's not true. Okay, this one. So can you see how both of the methyl groups are pointing up? If we flipped one of these,
Yeah, I have to go for a try.
okay, good luck.
Thanks.
So these are pointing, one's pointing up, one's pointing down. Now let me flip this one. So now I'm going to put this one going up and this one pointing down. So our methyl groups are on opposite sides now. So this would exist as this would be our trans and our cis isomer. So this would exist as a cis-trans isomer pair. So this one you just have to think through. If you can see it, you can just click. I sometimes have to think about it a little bit more.
So now that you're saying the top one right there
Uh-huh.
would be yes, so then the bottom one has to be yes as well.
Yes,
This is basically the same
Yep.
thing.
basically the same thing. Yep.
Okay, and then the other one off to the right, I don't think you could do that.
So let's see. So this is a little bit hard to see. So let me draw my. I'm gonna draw my double bond here. This is my double bond.
Oh no, it could be trans, could it?
Yep. So we could put our chlorines up and our hydrogens down,
And then it would,
or we could flip it.
And it could flip as well.
Yep.
So yes.
Okay. There. I think we need to. Oh yeah. No, we're good. Okay. This could be locked like this.
Yeah.
Okay. I think there is a. So I think so. This one could be. There is also a case where if you flip it, like this one, you could flip it, but you're going to get the same molecule. So just be careful, and that's because this group has the same groups on the one side. If you have two of the same group on one side, then that can't be a cis-trans isomer. Because you have the same. Okay. Okay. Last thing. We have these reactions called addition reactions. I think this is also on your sheet. Your review sheet. Do I have? Yeah. Okay. So if we have a double bond, these are pretty reactive. So a lot of the time when we're doing chemical reactions, we have some kind of reactant group, and then this is called addition. We're adding this molecule across the double bond. So what happens is one of the pieces of this simple molecule goes on one of the carbons, and one goes on the other carbon. So we're breaking this bond. We're actually breaking this bond too, and then we're forming two new bonds. So the X part is going to go on one side, the C part is going to go on the other side. So that's what's called an addition reaction. We're adding the molecule across the double bond. That's a pretty common thing people say. And I think this picture is on your note sheet.
It's, yeah, yes.
You guess? Maybe I didn't
Yeah,
put it
it
on
is.
there.
Yeah, kind of.
Oh, okay. So then we have two types of addition reactions. So the two types we're going to talk about are on your sheet. We're going to talk about hydrogenation and hydration. Have you heard of hydrogenation? So if you take organic chemistry, you do a lot of this kind of thing where you're like, oh, I have this molecule, I'm going to add something, and then you have to predict what the product is. That's a lot of what organic chemistry.
Do you just do it on the bricks out here?
Yeah.
Okay,
Yeah.
like center of the tennis court?
No, on the retaining wall. Okay, so this is a whole bunch of different alkene addition reactions. We're gonna talk about hydrogenation and hydration, but there's some other ones. So you can add a halogen across the double bond, or hydrohalogenation because we are adding hydrogen and it's a halogen. So in organic chemistry, you just learn about all these different types of chemical reactions, and then you also predict the geometry. So depending on what you're adding, it likes to add in certain spots. So you can be like, oh, well, if there's a methyl group here, this chlorine is going to not want to be next to the methyl group. It'll add over here. So you can predict your products. And so a lot of organic chemistry, if you have to take that, is like stuff like this and memorizing patterns about how things will add. Okay, so we have only two that we're going to look at in our class. So hydrogenation, this is the one that is on your paper. So just like in the note sheet before, the slide before, we take our double bond, we add hydrogen, and we're getting rid of the double bond. The double bond is breaking. We're breaking the hydrogen bond, and the hydrogen atoms are making bonds with the carbon. Okay, so we had our alkene, now we have our alkane. Oh, the other important thing is that we use a metal catalyst. So usually we use something like palladium, or palladium on carbon is a pretty common one. What else do we use for hydrogenation? I think platinum works for this. I do this one time in graduate school, and my catalyst was a palladium on carbon catalyst. Okay, so in hydrogenation, so we're adding hydrogen across our double bond. We need a catalyst. Okay, yeah, we usually use palladium on carbon, palladium, nickel and platinum, great. And the catalyst just makes this reaction faster. It just facilitates the hydrogen bond breaking and then adding those hydrogens to the carbon-carbon double bond. Okay, and then back to stoichiometry. We talked about stoichiometry in chapter 5. We need one hydrogen for every one double bond that we form. That makes sense, right? For every double bond, we're going to put one hydrogen on each of the carbons. So we need one hydrogen molecule for each double bond to be able to hydrogenate all the molecules that we have. Okay, so that's pretty straightforward, hopefully. Okay, so here is the question. How many hydrogen molecules would be required for hydrogenation of the molecules shown below? So about the top one, how many hydrogen molecules would we need to hydrogenate the top molecule? think it's 10.
Really? No.
Yeah, 2. Yes, you're right. Can you tell us why you think that?
Because I see 2 bonds,
Yeah.
and you need a pair of H2 to get rid of 1 bond.
Good, perfect. So for each of these, we need 1 of those, and there's 2 of those, so we need 2 of those. Good.
And then on the bottom one is the same thing.
Yep, same thing. Yep. Yep. So this is called a conjugated bond because it's like 1 away. This is an isolated because they're not 1 away.
Yeah.
So if it's conjugated, our electrons can move through this whole system. So that's something else you would talk about in organic chemistry. These electrons are really, they're stuck. And in a conjugated bond, the electrons can kind of move around a little bit more. Okay, the last topic is hydrogenation. So this is where we're adding water across the double bond. So again, for every 1 double bond, we need 1 water. We use sulfuric acid, we use an acid catalyst. So if we add a little bit of sulfuric acid that acts as a catalyst, this helps it speed up. And then if you took organic chemistry, you talk about the mechanism. How does this catalyst help this reaction go faster? And you can draw things that's called arrow pushing, and you show, oh, well, this doesn't have enough electrons, it's going to pull the electrons, and it helps the reaction go faster. But we're just going to kind of memorize what's happening. So same thing, one of the hydrogen and oxygen bonds is going to break, the double bond is going to break, a hydrogen is going to go on 1 carbon, the OH is going to go on the other carbon across the double bond. And then we get an alcohol. So if we start with a double bond, we add water, we're going to get some kind of alcohol. Okay. Oh. So I think the examples that I've given you have H2SO4 or sulfuric acid, but you can also just put H+ to show that this is in the presence of an acid catalyst. Acid catalyst will make it go faster. So this is just like the very, very tip of organic chemistry. If you take organic chemistry, just like the regular organic chemistry is a whole year class. It takes 2 semesters. And you talk about all sorts of things like this. And it's just a lot of memorizing or just getting really familiar with all of these topics. Molecules. Okay, I think this is our last topic. There might be one more piece that we need to talk about. I can't remember. Okay, this is the last part. So if the carbons are identical, then it doesn't matter where they go, because you're going to make a symmetrical molecule. So if you do this, you add the hydrogen here, or the hydrogen here, and the hydroxide here, or the hydroxide here, it doesn't matter. Okay, that would be equivalent. But down here, we could either add the OH to this carbon, or we can add the OH to this carbon, and then the hydrogen would go on the other carbon. And so we are going to use this rule. If the carbon atoms are not identical, then the OH is going to add on the more substituted carbon. So it's going to like crowd it. We want it to be crowded. This has to do with what carbon has electrons when this reaction is happening. So the most stable product is where we put the OH on the more substituted carbon. The more crowded carbon will get the OH. The less crowded carbon will get the H. So we can predict which molecule we will form. So So usually in organic chemistry, there's like a major product, and then there might be some of the minor product. When we're doing our homework, we're looking for the major product that follows this rule. This is called Markovnikov's rule. So the OH, again, is going to add to the more substituted carbon if they're not identical. Okay, does that make sense? Okay, hopefully that makes sense. Okay, so if we have this, what would our product be? We're predicting this one is not identical, so it does matter where the OH ends up. So basically our question is, we know this is going to split off and we're going to get an H group and an OH group on our double bond somewhere. So we just have to decide, and the only places this can add is this carbon or this carbon, because it has to be attached to the double bond. So we're just deciding, does our OH add here or does our OH add here? So based on Markovnikov's rule, that we just looked at the other slide, where will the OH add? The
Carbon.
Yep, this on the top. Good. Up by this methyl group. Good. So this one, it'll add up to here because we have this extra methyl group. So our OH, our product, will be this hexane with a CH3 group and then an OH group here also. And then we don't have to draw this because that's a hydrogen now.
So this is the Markovnikov's rule.
Markovnikov rule. Yep. OH will add to the more substituted carbon if the carbons are identical. Yep. Good. Okay. That's it. I think that's the end. Oh, here's another one. What's the product? This is backwards. Then I think this is it.
Is it just pentane?
So we need a double bond somewhere.
Wouldn't it go like right by the OH?
Yep. So this one I think could have
2'
two
hexene.
products. Yep. So we could have this. 1, 2, 3, 4, 5. And we have our methyl group. There's a methyl group here. We could go here. Or this one could have a different product, or starting. We could also have the double bond here.
That's what I was about to say, the top one. I was about to say like right there. They go both.
Yep. So this could, either of these would be a good starting material to get this product. Because either way, this is the more substituted carbon, and you're going to get the OH here. Thank you. Maybe it's
Your dad is like just an opposite of the
Oh, so
I think
there's
this is our last slide. Sorry?
So there's a methyl group on.
Yeah, that's right there.
Okay, so there's 3' methyl dash hexene. Yes.
Okay.
Perfect.
Thanks. All right. See you. Okay, and that's the end of our slides. So you have 25 minutes left. Remember, Alex is due on Sunday. All right, we don't have a lot of time because we only have 2 days of our chapter 13. The lab 34 is due on, when does the lab due? The lab is also due on Sunday. So if you haven't, has everyone turned the lab in, lab 34?
I need to still turn it in.
Okay, turn it in. Turn it in.
I
And then
too much
we also have the signature assignment, Alex chapter 13, study for the final. Lots of teams.
I gotta go help run the junior high track meet today.
Oh, okay. Is there someone I should